Our project, Detecting Emotion in Audio Files Using Emotional Indicators, involves a deep learning algorithm to classify emotions of audio files from MEL frequency septual coefficients and the emotional indicators, valence, approach motivation, and arousal. Emotion is an incredibly important part of human communication that can change the meaning of a word, sentence, or phrase, especially in speech. Emotion is also a complex biological state that can be difficult to determine. In many real-world scenarios, emotion detection makes a huge difference in the outcome of the situation. Systems that sufficiently implement emotion detection have the power to preemptively stop criminals, advance online education tools, and improve the daily lives of people with various disabilities. Today, emotion detection exists in applications such as healthcare systems, but mainly rely on straightforward text inputs and limited choices rather than speech. Detecting the emotive state of a speaker will be an important milestone for the development of an accurate natural language processing system. Before we dive into our approach, let's define some important terms used in our project. First, an emotional response can be divided into 3 indicators. These values appear as outputs in our algorithm. Valence refers to the contrast between states of pleasure and displeasure in a voice. Arousal refers to the contrast between quiet, low states, like relaxed, and louder, high states, like surprise. Approach motivation refers to the contrast between the amount of urge one has to approach stimuli. For example, higher anxiety is an example of a low approach motivation state. Another term to define is MFCCs, which stand for MEL frequency septual coefficients, and are used as the input to our neural networks. They are derived from a type of septual representation of an audio file and are based on the MEL scale, which is a more approximate representation of the human auditory system's response than a linear scale. They are commonly used in speech recognition systems, so there are several existing libraries that calculate these values for a given file. Most of the research centered around emotion classification involves humans classifying them based on intuitions obtained from constant emotional experiences in daily life. In order to train a machine to exhibit the same intuitive level of emotion recognition, we used all 3 dimensions of the previously mentioned emotional indicators. Most emotion classification research using machine learning has been done in just 2 dimensions, considering only valence and arousal, rather than all 3 like in the image here. Furthermore, prior research has mostly revolved around the audio file without considering the corresponding text. We wanted to combine results from audio and text files to result in more data and help increase the accuracy of emotion detection, which several existing studies lack.
We considered 6 emotions in our classification: happy, sad, neutral, anger, disgust, and fear. Based on our research, we determined the ideal valence, approach motivation, and arousal for each emotion. Each value is an integer ranging from -4 to 4, inclusive. A negative value means a low level of the specified indicator. 0 means a neutral level, and a positive value means a high level. The dataset we used is called CREMA-D. It contains 7,442 original voice recording clips from 91 actors. The set is almost evenly split between male and female, with 48 male voices and 43 female voices, all between the age of 20 and 74, with varying races and ethnicities. All the actors spoke 12 sentences with 6 varying emotional states, and finally, the emotional states were then labeled based on a crowdsourced effort of 2,444 people who each rated the emotional states of a clip and their intensity. We personally did an 80-20 split of the data at random using the scikit-learn library. We have quite a long ML pipeline to discuss, so we will split it into 3 parts in this presentation: data pre-processing, the neural nets themselves, and then the graphing of the emotional indicators. The first thing we'll discuss is the data pre-processing. As said previously, we use the CREMA-D audio files as our training and testing dataset. We converted the discrete emotional labels into labels for each indicators, then extracted the MEL frequency septual coefficient from each of the files, and finally transform the MFCC data to display emotive speech patterns more clearly. We then trained all 3 neural networks on 80% of the data. A little bit of detail on the neural nets that we constructed. We built a one-dimensional convolutional neural net because the data we used is a time series dataset, and therefore only needs to be processed along one dimension. We built each neural net individually for every emotional indicator. However, each emotional indicator spanned over different ranges over each emotion. For example, valence only had 4 possible values based on the emotions present in the training data, meaning that the last layer of the neural net had to only contain 4 nodes, unlike arousal that had all 9 indicators, because the actor specifically spoke in emotions that had high arousal and low arousal. This ended up meaning that each neural net had to have a different amount of layers according to the range of indicators they would output, since some of the emotional indicators will have nuance in the data more than others. We then use categorical cross-entropy as our loss function to derive the expected value of each of our ratings. We also use an SGD optimizer for faster convergence because the training set was taking a very long time to converge. We finally ran all 3 neural networks until they reached an arbitrary accuracy of 97%. Once the neural networks are trained, we tested the data on a portion of our audio files, obtaining probability for each rating. We calculated the expected value for each of the indicators, obtaining a 3-dimensional vector representing the emotional indicators. We then plot the indicators on a 3D graph. We run KNN with one neighbor on the data set with the training set for KNN consisting of all 6 emotional indicators points to derive clusters and get this graph. This is our testing data set with each of the labeled emotional indicators on the top left. An interesting thing to note here is that the clusters with very large ranges, they are clusters in the middle and therefore contain more emotionally neutral data points like sadness and neutrality. This would imply a difficulty for the model to predict emotions with no obvious emotional indicators. I will now show the machine learning algorithm in the works. Firstly, I'll give an example of an audio recording where I'm very angry.
I am so angry.
As you can see, I am very angry. And I'll run the algorithm. Since it's labeled anger 4, I'll put in anger 4 right there. And it ends up labeling our vector as negative 2.9, positive 2.9, and positive 2.9, which almost exactly hits the anger point. Now I'll give a less obvious classification. This time it's going to be called fear 3.
The quick brown fox went over the rock.
You can hear very high arousal in my voice, which may impact the classification of this fear. Now let's change the name, FEA underscore 3, and run the algorithm. Now this time I have very high arousal, but very low approach motivation, which would imply that the vector fear ends up being very close to anger, or sorry, very close to fear instead of anger, even though the valence is classified as negative in this situation. And this is actually a big strength of our model and the way we decided to do it by plotting separate points on the graph.
There are hundreds of emotions that exist and are less distinguishable than the 6 we considered for this project. Expanding the data set to consider more emotions and incorporate longer audio files while maintaining a high accuracy is a sensible next step for this research. Even though emotions are intricate, when accurately identified through machine learning, they can greatly improve the effectiveness of interactions between humans and technology.